Everybody, so I'm going to show you how to figure out Huggy Bear's weight based on the tension vectors that we saw in class. And if you didn't see them in class, I'm going to remind you. We hang Huggy Bear from a string, then they were secured to the ceiling. The tensions on the spring scales were at 33 newtons, and the angle between the strings, I believe, was 110 degrees. And we wanted to figure out what the weight of the bear is. And the whole point of this exercise is to introduce the idea of taking forces and breaking them up into components so we can compare vertical to vertical and horizontal to horizontal. So if we look at an FBD, of course we have FG on the bear. And then the strings have tension in them, and I'm going to draw some arbitrary tension vectors. I want you to understand that the length of the string has nothing to do with the length of the tension vector. Okay, so I'm just going to draw an arbitrary I'm going to call it T here, and then there's another T here. And we understand that both T's are the same. So we know that this system is in equilibrium, meaning the forces have to add up to 0, but we can't just say T plus Fg equals 0. We want to compare vertical to vertical and horizontal to horizontal. So that's where sigma Fx, the sum of the forces in the x direction, and we want to do that. So we know this has to be 0, and this has to be 0. So in order to work out the algebra, we want to break things into components. So I would take this component, and I would call this Tx, and I would take this component and call it Ty, where the relevant angle here is theta. And that's the same as that theta up there, the angle that the string makes with the ceiling, or the angle that the string makes with the horizontal. We're going to learn how to figure that out from geometry in a second. Okay, it's not going to be the 110 degrees that we measured, but it's related to that 110 degrees. If we do the SOHCAHTOA, what we can see, and I'm just going to do it right here, that Tx is nothing more than the tension vector times the cosine of the angle that we have in our triangle. In other words, this tension vector right there is the adjacent side of the angle, and we know that Ty is equal to the sine, the tension vector times the sine of that angle. So work that out for yourself. Make sure you can do that, because at this point, this is something we can do without having to derive it every time. But if you still don't feel comfortable with that, make sure you do that. So I'm just drawing the other two components, and I might call that, Tx1, Tx2, or excuse me, both these called 2, and the first one's 1. Anyway, what we can see by all these components is that in the x direction, we see that Tx1, I didn't label it as such, but this would be 1, plus Tx2, well, how can I put that? Yeah, the sum of those two is 0, meaning one is the negative of the other. So if we wanted to calculate the horizontal tension, that would simply be 33 times the cosine of the angle. So I guess I should define that angle right now. Let me draw the strings over here. So we saw that this was 110 degrees. I know it doesn't look like 110, but anyway. So if I want this angle here, I think we can understand that if this is 110, these two angles plus this third angle have to add up to 180 degrees. So these two angles are going to be the same, and if 180 minus 110 is 70 degrees, I think that's right. So this is going to be 35 degrees, and this is going to be 35 degrees, such that I get a total of 180. Okay, so this turns out to be 33 times the cosine of theta, which is equal to, or equivalent to, 33 times the cosine of 35 degrees. And if we punch that out in our calculator, I should have done that beforehand, but that's all right. I'm assuming I'm in degree mode. It's about 27 newtons, pulling it to the left or to the right. Now, what we're really interested in is the y components. So what we can see from the force diagram is that Ty1 plus Ty2, those two vertical components, minus the weight, have to add up to 0. So in other words, if we're looking for the weight is nothing more than Ty1 plus Ty2, which is equivalent really just to 2 times twice the y, because we know that the y components are the same. And so how do we calculate the y component? Well, we already said that's going to be nothing more than, we got the 2 from both components, times t, the actual tension vector, sine of the angle. And this derivation you want to be able to do. Understand that 2 is important because its 2 strings are supporting it. Okay, so if I do the 2t sine theta, so I do 2 times 33 times the sine of 35 degrees, I get 37.8, or about 38 newtons. So the weight is 38 newtons because it's equal and opposite to the two vertical tensions. And that's really what most of these lessons are about. Okay, so important summary. In equilibrium, horizontal forces are always balanced, and the vertical tensions balance the weight. So with two strings, there's two vertical tensions. Don't ignore the factor 2. Now, what happens when the hanging angles aren't the same? That's not easily done, but you can imagine that one string is higher than the other, but I haven't drawn it here. So I have theta 1, I have theta 2, and the important thing I think in this one is the way I've drawn it, theta 1 is less than theta 2. Okay, once again, this is an equilibrium. So if I draw components, I have to draw it such that the horizontals are the same. There's no way they can't be the same. So they're going to be equal and opposite. Okay, and they would still go by the tension times the cosine of the angle. It's just that the tensions aren't going to be the same as each other. That's the first point you want to make. When these are unequal, the tensions can't be the same. So the string with the greater tension is the one that has the greater vertical component. There's no way they can have different horizontal components because otherwise the object would have to accelerate to the left or right, which doesn't jive with the idea of being in equilibrium. And what we can understand is the one with the greater hanging angle is the one with the greater vertical component. So when I go to draw these, okay, I've already drawn this vector smaller than this vector because I know because it has a smaller angle, it has a smaller tension. And so now I can see that if I draw the y components, this ty2 is greater than ty1. And the way you can understand it conceptually is this string is just supporting more of the weight because it's more vertical. Okay, so in this example above, we have T1 is equal to 10 newtons, and the angle is 20 degrees. T2 is 40 newtons, so it's 4 times greater. What must be the value of the second one? And we basically can figure that out because we can say Tx1 equals Tx2, because we know that the horizontals have to be same as each other, so x1 would be 10 times the sine or cosine of 20 has to equal 40 times the cosine of theta 2. I'll let you work out what that angle is. It's a good exercise using it. And then if I ask what's the weight of the angle, that weight, Fg, we know is balanced by the vertical. So it's Ty2 plus Ty1, which is T1 sine theta 1 plus T2 sine theta 2. Once you have theta 2, you can plug in numbers. And again, you can check your answers. Okay, the next tutorial we'll do the second page of the notes, which is kind of similar to this, but a different situation.